Good morning friends, this is Sanjay Churiwala. I work at the Hyderabad office of AMD. I want to thank you all for attending this session. In this session, we will talk little bit about RTL based methodology to give an exposure to what this methodology is. I will not, my conversation here is in my personal capacity. We will not talk about our products, AMD products, or the methodology that AMD follows. Nothing specific about AMD technologies. The main purpose why we agreed to this talk is to do this kind of talk is, in general when people think of semiconductor design, they always think in terms of it is very complex. People think billions of transistors and then they get worried, right. I often get calls from my friends saying, will my son be able to understand electronics, will my daughter be able to study electronics, right. With this talk we wanted to show, while we hear of semiconductor being very complex, there are lots of methods and techniques in order to make sure things work well. It is not as if you yourself will draw thousands or billions of transistors yourself, right. So, you will hear me talking about many things. All that is not to scare you, but rather to tell you what kind of support system exists around you when you enter into this field. So, hopefully at the end of all this, you will be able to see little bit of what kind of techniques and technologies are used, and you can come in much more confident into this field of semiconductor design. So, before we go into RTL itself, I want to look at the whole semiconductor space, the whole process of semiconductor manufacturing, and I will go from backwards to front side, right, backwards to front. So, this is what happens when there is a wafer. The wafer is composed of many dies. So, once the wafer is fabricated, each die is individually taken out. The wafer is broken into multiple pieces. So, you are seeing these orange pieces, these are each dies, and then each of these die is tested individually, and after testing individually for any manufacturing defect, it is packaged, and that is what you see in the market, what you know as semiconductor or IC or chips. So, this is after the fabrication has happened, and this technique is called OSAT, outsourced semiconductor manufacturing and semiconductor assembly and testing. Okay. There are companies like ASIC which work in this area, Keynes Technology, ASIC, etc. So, before the semiconductor wafer is available, this is what is the actual fabrication process. There is a blank wafer which has multiple layers of chemicals, and we put in a photoresist element, photoresist material, which means material on through which we cannot have light related actions. Through concentrated rays, we remove photoresist elements from some area, which is what you see the red portion on the figure, that is where the photoresist element has been removed. What this means is, now if you scatter an doping, the doping will affect only the red portion, and the blue portion, which is the photoresist material, that will not allow the doping to affect the material. So, effectively after the doping, you have some transistor layers created, the photoresist prevented the doping at some places, other places doping happened, and we will keep doing this multiple places to establish the metal connection and so on, and through multiple layers of etching, doping, etc., we would finally get the semiconductor wafer done. This kind of work happens in companies like, say, TSMC. Now, before this, before the wafer fabrication, we do something called tape out. This is where the actual design happens. In our country, this process is this happens at a lot of companies. There are many companies in India which do this work, and when we talk about semiconductor design, semiconductor industry in India, a lot of it is related to this process, the design process. In the design process, we start with system specification. Somebody will specify what exactly do you need. From there, somebody will do the architecture design, what portion should be done in hardware, what portion should be done in software, what should be on chip memory, what should be on off chip memory, and so on. And then we will do the basic logic design, verify the logic design. At this stage, there will be iterative process to verify correct, and so on. And then we go to physical design and physical verification, and then it goes to chip fabrication, which was the previous slide that we saw. In very broad term, the physical design and physical verification, this process is also called back end, and the basic logic design and logic verification is also called front end. In very broad terms, that is what happens. Now, what we have shown is a very simple simplified diagram of this whole thing, but in reality each of this step is very involved. And today for the next around 70-80 minutes, we will talk mostly about the two blocks here, the basic logic design and the logic verification. Okay. And once again, don't get too alarmed when you hear various things and so many steps involved. All this is mostly to show that there is enough support system, tools, etc. Nobody is doing billion transistors by hand, right. So, when you hear people talking about so many transistors, you should not get too worried that whether this field is for you or not. Now, my presentation is mostly an engineering presentation. What this means is typically black and white, not too much colorful, which usually comes from various marketing slides, etc. And I have also copied several images from internet. Wherever I have copied those images from internet, I have mentioned this to give due credit to the fact that those are not my slides. So, let us now come to the basic logic design. So, today's technology, most of the basic logic design is done in RTL design. Okay. RTL stands for register transfer level. Now, RTL design is distinct from switch level modeling or gate level modeling or behavioral modeling. Switch level modeling, switch is often used in semiconductor circuits to mean transistors also. So, switch level modeling means you can specify something in terms of transistor. When you talk about an inverter, you could write an PMOS and an NMOS and connect them together, and that becomes inverter. So, that is the switch level modeling. Gate level modeling is when you write something in terms of the AND gate, the OR gate, the flip flop, D flip flop, and the XOR gate, and so on, right. And the behavioral modeling is still higher level of abstraction, where you talk everything in a very high level of algorithm, almost like a same level as say C. So, RTL design falls somewhere in between. It is between gate level modeling and behavioral modeling. Now, all of these, the switch level, the gate level, and the behavioral and the RTL, okay, they can be simulated. You can apply vectors and see for what kind of vectors what will be the circuit's response. And all of these are legal HDL. HDL stands for hardware description language. Typically, Verilog and VHDL are two popular languages. I would often talk about Verilog here in the context of this presentation, but you could just easily replace Verilog by VHDL. So, all of this switch level, gate level, RTL, behavioral, all these are legal Verilog, legal HDL, and can be simulated. However, RTL is special among these four because behavioral models, while you can simulate, you cannot synthesize, and we will talk a little bit later as to what does synthesis mean. And the switch level or the gate level, they do not have very high degree of abstraction, they are much lower level designs. You might as well do handcrafting of the circuit. So, there is no extra advantage of RTL design methodology. So, this is why the RTL based methodology is much more popular in the current design techniques, current world of design techniques. So, let us see little bit of what does this mean. So, first use of RTL model is simulate. We talked little bit earlier that we can simulate all kinds of circuits, all kinds of modeling abstraction. So, why do you want to simulate? To verify that I have achieved the functionality that we desire. I have certain functionality in mind, I wrote the description of that functionality in the form of RTL. I have to simulate it to make sure that the functionality is achieved. It is not giving an incorrect functionality. And the reason why functionality could not be achieved could be because we have not approached the problem correctly, our algorithm is incorrect, we have not coded it correctly, or whatever, right. So, whatever we have coded is what we will realize, and we want to verify that we want to use simulation to verify that the functionality is correct. Simulation pretty much means you have a circuit, you apply a bunch of zeros and ones at the input of the circuit, and you observe what is coming out at the output of the circuit. If that output is in line with what you want, then you know it works correctly. If it does not, if the output is not in line with what you want, simulation also allows you to probe internal signals of that whole block. So, it is easy to debug. So, simulation is one major usage, and since RTL description is, and you will see, we will see an example how RTL description can code much faster, which means we can validate our circuits much earlier or our algorithms much earlier. Also debug is easier because like I said that the simulation allows us to probe signals inside a block and module also, something that may not be very easy on hardware. The other major usage of RTL model is synthesis. What synthesis means is you have an RTL description, you take it through a tool called synthesis tool, and at the output you get a gate level realization. Okay. So, for example, you could say count is equal to count plus 1, okay, which is a counter, and at this when you send this to a synthesis tool, at the output you will get the D flip flop, the JK flip flop, the logic which is required to realize the counter, things that you would have usually done through your K-map kind of circuit, K-map kind of design. The idea behind synthesis, once you have written the RTL and verified the functionality, the mapping of that functionality into digital logic can be done by the tools instead of somebody else spending energy, instead of a designer spending energy. So, fundamentally this is what we are talking about. We write the RTL in a Verilog or VHDL, both of which are called HDL languages, and we write a test bench. Test bench is the one which is applying vectors at the input. Vectors means zeros and 1. For example, if you have written an RTL for a counter, so your vectors could just be repeated clocks. Okay. And simulation is the process where the tool simulator is used, where we read the design, the RTL design and the vectors, and simulator tool will tell us what will be the corresponding outputs. This process is iterative because the simulation tool tells that the results are not what we want, then we might want to go back, debug and fix our RTL and again simulate and so on. At some stage we will be happy that our RTL is correct. This RTL realizes the functionality that we are interested in. Now, when somebody is writing an RTL, they can also make mistake just like anything else. Any design mechanism, anything that you think of, a designer could potentially make mistakes. These mistakes could be he wrote something incorrectly. The mistakes could also be that they missed by taking care of something. Now, also understand, right, when we looked initially at the diagram, logic design is the first stage of the design process. After logic design, there will be physical design and so on. So, it is possible that if we do something at the RTL stage, at the logic design stage, there could be implication at the back end stage of the design process. And if there is a new user, not a very experienced designer, they may not be able to think of all possible implications. If I am doing something, what is the implication at the second stage or third stage or fifth stage or seventh stage kind of thing, right. It is very example to if you are creating a building, if you are constructing a building, you do something at the foundation stage and its impact will be felt on the 8th floor also, right. So, if it is not a good architect, they may not know the mistakes that they are making at the foundation stage till they reach the 8th floor. So, similarly in the RTL, somebody could make mistakes because of lack of knowledge of domain knowledge of the of expertise. And there are some examples, for example, you want to write a shift register. In shift register, the value moves from one register to the next register to the next register to the next register and so on. But if you make a mistake in RTL coding, the shift register could get implemented as an feed through. What that means is at one clock edge, the value moves from not one register to just the second register, but it goes through multiple registers and goes there. Okay. Or somebody could do clock gating, which is not done correctly. If clock gating is not done correctly, then what happens is something called spurious clocking, which means clocks will start showing up at a place where they should not show up. Or the functionality that you wanted to realize is different from what you actually ended up realizing because of your RTL mistakes. There is something called ATPG. ATPG stands for Automatic Test Pattern Generation. We will get a little feel of that slightly later. But if your design is something which does not lend itself to ATPG, then the testing of the devices is not very easy. So, you want to create your design in a manner so that the testing is easy, which means the test pattern generation is easy. Again, something that we should take care of it at the RTL stage itself. And then there are reliability issues also. We will often hear something, and you may have also seen at your home some instrument does not work, you turn it off, turn it on and starts working. These are because of reliability issues on those electronic instruments. Clock domain crossing is one of the reasons which causes, unsynchronous clock domain crossing is one of the reasons which causes reliability problems. So again, these are kind of things that one has to take care of at RTL stage, and if they don't take care of it at RTL stage, then the effect could be felt much later. For example, the last one, the reliability issues, the effect will be felt when you take your device, run the device on the hardware multiple times. Sometimes you will see reliability issues showing up once in 600 times and so on. So that is after the device has been fabricated is when you get to know of it, right. So we want to make sure that all these mistakes are taken care of at the RTL stage itself. We talked about simulation, which will catch some of these, but not necessarily all of these. So then here is an example where we talked about the shift register versus feed through. So I want to make a shifter, and if you look at this code, this is a Verilog example and this is an incorrect example. This code says that signal A will go to, the value of A will go to B, the value of B will go to C, and the value of C will go to D. Okay. So it looks like it's a shifter, that is what it looks like, that each value is going to the next register, right. But in reality it is not shifter. In reality the value of A is going to everything into B and C and D. It may not be very apparent to somebody who is not very experienced Verilog designer. Let us look at another example. This actually is a shifter. If you look at it, what we have done is we have just changed the order of the assignments, the signal assignments we have changed. What was in the first line has gone on to the last line, what was in the last line has gone on to the first line, and so on. Okay. So this will actually work as a shifter, but this is not a very good shifter because this kind of code is not easy to maintain and port. Okay. If you tomorrow want to make changes, this kind of coding style is not good. So let us look at some more coding styles. This is a valid shifter, okay, and so is this. Okay. In fact, both these codes are equivalent. Here also if you see, we have changed the order, but they both will work correctly. Now in case you have not noticed, what is the difference between the previous slide and this slide is the assignment construct. Okay. In the previous slide we were using the is equal to symbol. In this slide we are using the less than is equal to symbol. In the world of Verilog, the is equal to symbol is called blocking assignment, and the less than equal to symbol is called the non-blocking assignment. Okay. Again, this is not a tutorial on Verilog, so we will not be able to get into the details of it, but the point is we wanted to create a shifter. We had two codes earlier which seem like a shifter but are not shifters, but first one is not even shifter, the second one is shifter but not easy to maintain. You will realize that implication when you create another design variant of it. The second one is the proper, this slide has a proper shifters. For somebody who is not very experienced, how will they be able to understand this kind of difference? Okay. So there are tools which do this kind of work. Okay. So these tools are called lint tools or linter tools. So linter tools, they catch coding styles which seem to be reasonably okay, but will most likely create a problem at later design stages, right. So that is the idea of linter tool, that catch coding styles, code constructs which seem to be reasonably okay, but will create trouble later on for your design cycle. So the example that we saw, any reasonable linting tool will flag the first two examples, the one that where we had used the blocking assignment, just the is equal to assignment, because it will be expecting a non-blocking assignment. Okay. So this is just to show that okay, if you make some incorrect coding, there are tools which will help you catch those till you become an expert yourself. So linter tools are used mostly as a review tool, so that the more experienced designers, they can work on complex things. Okay. And the less experienced designers, when they are starting their career, they can use linter tools to do a quick code review. Right. That is what this is, an automated code review. Linter tool is using the code review, and then the experienced designers don't have to spend time reviewing the code of a less experienced person. Rather, they can spend their time in things where they can actually bring value, the algorithm, the logic, and those kind of things. Linters are very useful to folks who are new to RTL, because since I am new to the RTL world, new to the semiconductor design world, I may not know what could be the potential implication at the later stages of the design flow. So, linter tool will help that. Okay. And linter tools, I will see in the next slide probably, the linter tools also grow based on the design knowledge. Okay. I learn something based on a mistake, I can code that learning into a linter tool, so that any other design in my company can make use of that learning. The linter tool will use that learning to check for other people's code also. So, we talked about RTL and we said we will use test bench and we will use simulator to verify its functionality. One more round of verification will be done using assertion based or static checkers. Okay. Here what happens is we do not provide any vectors. Linters are also called static checkers. This is because there is no simulation involved. It looks at the code and then checks whether this thing looks right or wrong, kind of thinking. And assertion based is, as you are designing your circuit, you might put in that this is my intent, and some assertion tool can check whether that intent is being met or not. For example, you could say, again using counter as an example, you could say after 10 it should give 11, right. So, that is an intent. So, the assertion checker will check that given the circuit realized, will it actually give 11 after 10 or so on, right. So, RTL we verified earlier using simulation. After simulation we would run assertion checker or static checkers also, which static checkers also means linters. Coming back to the lint tools, we can run lint tools at RTL level, at synthesized netlist level, at scan inserted netlist level, post layout netlist, etc. We will talk little bit about what is the synthesized netlist and what is the scan inserted netlist slightly later. Post layout netlist will not talk much, but again think of it that after the design has been placed and routed, the netlist that gets created out of that, the digital connection, the gates, that is called the post layout netlist after the placement and routing. When we talk about lint, while linter tool can be run at RTL level and all kinds of netlist level, it is most popular at RTL level. Okay. Again, logic is very simple. At RTL level, you want to catch your errors much upfront, and that is why lint tools are very popular at RTL level. So, lint is a very generic word, and like I was saying, it includes the knowledge base keeps on building. So, lint rules have been created as a collection of rules defined by Verilog. Verilog was a company which came up first with the original lint more than 2 decades back. So, they defined certain coding rules and coding guidelines, and that is what got converted into tool based checking called lints. Then there was a book published called Reuse Methodology Manual. Again, it talked about multiple coding guidelines which said that if you follow these coding guidelines, it will be easy for people, for the designs to be maintained, to be reused. You created one block, I can use this block into another block. So, that book Reuse Methodology Manual, all the coding guidelines from that Reuse Methodology Manual came into as lint. Okay. Meanwhile, if you have any questions or doubts, please feel free to call on the number on the scroll below. We will take questions live and also towards the end, whichever, whatever you feel comfortable with. If there is something is not clear, please feel free to call at the number below. Besides this Verilog and Reuse, there is a Stark. Stark is a consortium of I think 7 Japanese companies. They also came up with their coding guidelines. So, those are also coded into lint, and besides that, a lot of companies will have their own coding standards. So, based on those requests also the lint rules get developed. So, the point is all this knowledge on reuse, on the coding guidelines, etc., that get coded into something called set of lint rules or lint tools, and your HDL or RTL you can run through these lint tools to make sure that it is following the various coding guidelines. Okay. So, we were able to verify RTL using simulation, using assertion checker, using linters, using static checkers. Let us look at some advantages of RTL models. So, why will somebody write RTL models? So, one is higher degree of productivity. Instead of you writing your K map and then trying to identify the gate level logic, you can have the synthesis tool do that work. You concentrate only on the algorithm portion of it. So, effectively a huge improvement in productivity. We are talking about a different scale in terms of productivity improvement compared to if you had to hand draw this yourself. And later on we will see an example of a weird counter, and you can easily see if you had to draw that counter yourself using the K map and the digital gates, how long will it take, versus if you were to write an HDL, how small that code is and how easy that code is to read. So, what will the expert designers do? If simple designers can work through synthesis, etc. If there are more complex blocks, for those we can make use of the expert designers time. Maintenance. RTL models are easy to maintain. When you read an RTL model, it will seem almost like an English language. So, obviously it is easy to understand what is going on, which portion of the code. Tomorrow if you have to modify something, you know what to modify where, because it is the code is very obvious to you. Also, the way the RTL model is written is because it is a bit abstract, you can get a bird's eye view of the whole thing together. You do not have to get into the details of whether this should be an AND gate and OR gate kind of thing. You can get a bird's eye view immediately. And if you get the bird's eye view, you get as to what is going on where. It is easy to update and make fixes and so on, right. So, that is the easy to why we call it easy to maintain. So, it provides productivity gain, order of magnitude faster, and it provides it is easy to maintain. So, let us look at something, right. Let us think of a counter which counts in this sequence. It starts with 3, goes to 6, goes to 5, 4, 2, 7, 3 and so on. Let us just assume that we are talking about this counter. Now, for any of you who is familiar with digital logic, try to implement this counter in through digital gates. You will be writing multiple K maps, and then you will be identifying the optimized Boolean equations, and then you will be writing the gates corresponding to those Boolean equations. But if I am writing in HDL, the corresponding code is very simple. Right? It is looking at count and then case of count. Based on the value of count, if 3, change the value to 6. If 6, change the value to 5. If 5, change the value to 4. If 4, change the value to 2. If 2, change the value to 7. If 7, change the value to 2. Okay. First, there are two things which are interesting here. One, the code is so simple. Second, the code is so obvious. The requirement was from 7 it should have gone to 3, while it is so clearly visible that from 7 it is going to 2. Right? You can immediately spot the error, that from 7 it is not going to 3, it is going to 2. Right? Imagine you had a digital gate based circuit, would you have been able to imagine that what will be the next state of the counter? It is not very easy to imagine that, it is almost impossible to imagine that. So, while writing the code, if I made a mistake, okay, it is so obvious that this code is erroneous, and default is so that it starts again with 3, right. So, it took a few minutes to write, that is all it will take to write, okay. And more importantly, the code is so obvious, you can spot any mistake very quickly. Functionality is so easy to understand. Now, imagine somebody comes and says, no, this is not how we want to do it. Okay. From 4 it should have gone to 1, and then from 1 it should have gone to 2. Now, if you had a digital gate based design, you have to redo your entire K map. Okay. Over here it is very simple. Make that change just in this code and you will be all set. You do not have to once again write your K map, design your K map and so on. So, if you want to make a minor change in the sequence in this circuit, in the sequence of this counter, you can implement that much more easily compared to a digital design. So, this is at least one one very major advantage of RTL based design, that you can write the code very fast and then use a synthesis tool to realize the gate level netlist. The code is easy to understand. The code is easy to modify. If you are making a minor change to the desired logic, the code is very easy to modify also. We talked multiple times about synthesis. Let us understand what is synthesis. Okay. So, synthesis is a tool where you give the RTL code, okay, and it will give you the gate level netlist. We will talk about few other boxes, right. So, that is a fundamental idea behind the synthesis. Synthesis tool, you feed in an RTL code, be it Verilog or VHDL, and it will give you a gate level netlist. When you talk about gate level netlist, this means the design in terms of digital logic. This design now after synthesis has the flip flops, the AND gate, the OR gate, the MUX, the XOR, and so on. Then we talk about constraints. Constraints is another input to synthesis. Constraint tells what are my requirements for the realized gate level netlist. Okay. Think of your car remote. Your car remote, it is not necessary that it has to respond in nanoseconds. Even few milliseconds is good enough. But the battery for the car remote should last longer. Okay. On the other hand, think of a processor system. There you want the performance to be very high, so that it operates in the range of gigahertz. While for power, you can plug it into the power outlet. So, depending on your requirement, you will tell the synthesis tool what kind of realization it should do. Should it do a realization, a digital circuit which is much faster? Should it do a circuit which is not necessarily very fast, but does not consume so much power? Or it has area constraints, right. So, we usually call it PPA, power performance area. So, constraints provides those requirements, that what is important for me and how important is that for me. And ASIC library is, if you are writing a netlist in terms of say AND gate, OR gate, what is that name of that AND gate in the corresponding supplier's system, right. What are the characteristics of those AND gate, how fast it is, how much power does it take, how many variants of AND gate does it have. So, that is ASIC library. So, you put your design, you put your requirements through constraints in terms of power, performance and area. You tell it that okay, if I am going to implement this design, it should be implemented in say LSI logics library or say in NEC's library or so on, right. So, that is the ASIC library, and at the output you will get a gate level netlist, a digital circuit which a lot of us are much more used to in your school and your classes. When you see the schematic diagram, that is the gate level design, that is what will be the output. I also mentioned here care about there is something called naming. So, you wrote your RTL, and in the RTL you had all these variables. When synthesis tool generates a netlist, it should retain the naming from your RTL onto the netlist also. Okay. Whatever objects existed in the RTL, it should try to keep similar names in the gate level netlist. And we will see slightly later why naming is important, but naming is an important consideration, not just the circuit realization, but you also want to make sure that the naming allows some kind of correlation, that this object in the netlist, what was this in the RTL, where did this object come from. We continue talking a little bit more on the advantage of RTL model. So, RTL is at higher level. We talked about PPA, power, performance and area. So, when you want to make those trade off, it is easier to make those changes at a higher level of abstraction, either through constraints or through RTL design, and the impact is also much bigger. Once you have the netlist, after that even if you are making some change, the impact can only be very, very minor. Okay. Again, think back using a house construction example. If you have a vacant plot, you can make much more changes to your design idea at that stage. But if you have already put the foundation and the walls and the right, after that you can make only minor alterations. So, similarly RTL is much earlier in the flow, it can have much bigger impact, it can make much bigger impact on the items of our interest. There is something called AND or invert. Okay. So, let me explain this. This is a bit convoluted or bit involved. Many of us are familiar with AND gate, OR gate, NOT gate, etc. One AND gate takes 6 transistors, one OR gate takes 6 transistors, and one inverter takes 2 transistors. But imagine a circuit where I have 4 signals going into 2 AND gates, and the output of these 2 AND gates can go into an OR gate, and the output of this OR gate gets inverted, AND or invert. Okay. We can realize this in, I think, 8 transistors. Okay. I might be slightly low, I might be wrong, but maybe, but much lesser number of transistors compared to if we were to do AND individually OR and then invert, right? AND or invert. So, synthesis tool can make use of AND or invert kind of gates. I am saying its variants because you can create lots of variants. Instead of AND or invert, you can have OR and invert, or invert and invert OR, and those kind of things. So, synthesis tool can make use of a lot of these gates, effectively realizing a functionality in much lesser number of transistors. Okay. Human beings, we human beings are not used to AOI style thinking. We are much more used to thinking in terms of AND gate, OR gate kind of thing. Okay. So, if we have to realize the same functionality ourselves, we will put in an AND gate followed by OR gate followed by invert, and that will take many more transistors. So, much less area, much more area, so much less efficiency in area and much more power. So, synthesis tools, commercial synthesis tools, they will make use of AOI very effectively in order to realize a much smaller circuit with lesser delay and better power profile, versus human mind, which will not be able to do that. In fact, you can try thinking, if you have to realize any digital logic, think of realizing in terms of AND or invert. It is not easy to think of it. It is much easier for us to think in terms of AND gate separately, OR gate separately, inverter separately, or you could do NAND and OR. That is also okay to realize with some practice. But thinking of AND or invert based expression are not so easy for human mind to think of, while synthesis tool can do it. So, effectively, if you write RTL and go through synthesis tool, we can get designs faster also, and also the circuit is much more efficient. So, now that we know that RTL based design is a better style, right? We have seen the advantage of RTL based design, and we know that this is a good style. What if I already have a design which is done in schematic form? Should I convert it into RTL or not, so that I can get advantage of the RTL? So, fresh design is very obvious. Fresh design, you should always go with RTL based style if possible, HDL based style, RTL based style. But if the design already exists, schematic based design already exists, should I make an effort to convert into RTL? Okay. Answer is yes, if the design is supposed to live for longer time. Okay. Because future maintenance, okay, if you want to make future enhancements, some fixes, some debug, the RTL based design, it will be easy, while the schematic based design will not be easy. If the design is all done, dusted, you are not going to touch it ever, then let it be. But if you think that you will be updating this design, you have to maintain this design for long, then you should consider migrating it into HDL or RTL. Once you have the RTL, the validation will be faster. If case you want to make some updates, it is much easier to make the update in the RTL, it is much easier to validate in the RTL, faster and validate. You want to migrate to a new technology node, you were working on 28 nanometer, now you want to move to 20 nanometer. Using that schematic only design, it is much more painful, but if you have an RTL, you have to run synthesis through the new library. So, migrating to a new technology node is also easy. And the circuit protection, there are certain things which are totally wrong in an electronic circuit. Synthesis tools will catch and prevent those situations inherently. For example, some electric rule based connections, right? Multiple drivers. You should not have multiple drivers for any given on any given wire. Multiple drivers can result in short circuit, contention, various kinds of things. A synthesis tool will not create a situation of multiple wires. Similarly, if there is a combinatorial loop, think of it, right? An inverter feeding another inverter, feeding another inverter, and so on and back to itself. Okay. If you have a loop of inverters with odd number of inverters, that circuit will never stabilize. Okay, it will keep on toggling continuously. Again, synthesis tools will identify and report these kind of weirdness in our circuit. So, when we go through RTL and the corresponding methodology, some of the protection mechanisms are built inside the methodology and the system. So, the point is, even if you have a schematic based design already existing, if you think that you need to maintain this design for a while or upgrade it or migrate it to a newer technology node, etc., please consider migrating that design into RTL based methodology first, and after RTL based methodology, then into RTL first, and after that use the RTL based methodology rather than migrating the schematic directly. So, now we want to migrate from the schematic to RTL, right? How can I migrate? I am looking at the schematic, I look at each element in the schematic and write the corresponding HDL. Okay. I see a transistor, write the HDL for that. I see an AND gate, I write the HDL for that. Okay. So, one-to-one replacement. Okay. But this is a very, very bad way of doing it. Yes, we have written the HDL, but it is still switch level or gate level. So, it does not give any of the benefits that we talked about earlier. The benefits we talked about earlier was to be able to make use of synthesis tool, to be able to write a code which is easy to understand, but if it is still switch level, it is not easy to understand. So, the right method is understand the logical functionality of that schematic and write the actual RTL for that logical functionality. Instead of doing element by element translation, understand the big picture and write the RTL for that big picture. Once you have the big picture captured through the RTL, now you can go through the RTL based design methodology. So, what we have talked so far was the advantage of RTL based design methodology, and also how we will take it to simulation and static checkers to verify that our RTL is correct, and then take it to synthesis to generate the gate level netlist, right. So far I have been talking about how RTL based design methodology is much better. So, does it mean that it solves all the problems? No, there are some. This RTL based design methodology also has some limitations, and we have not gone into the actual methodology other than synthesis. We will talk some more in a while. So, functionality that we realize in the gate level netlist after synthesis could be different from what we had seen during simulation, right. We simulated, we verified a functionality, we were happy. Now, we went to synthesis, and synthesis gave a gate level netlist, and that seems to have a different functionality. Okay. Why could it happen? It could happen because of what we call as race conditions, which typically means the code has not been written correctly. And it could also happen by something that is called simulation versus synthesis mismatch. Something was simulating one way and the synthesis results are different. These problems can happen, this kind of problem can happen because the code was not written correctly. Okay. The RTL code was not written correctly. So, the correct solution to this is to learn how to write a good RTL code. Okay. The problem is not in the methodology, the problem is making sure that we have the right skills to write a good RTL code. It is not a problem in the RTL methodology because if instead of RTL I was doing something else, let us say I was doing gate level design, I could make mistakes there also. Right? So, it is not that RTL methodology has the problem. the person who is writing the RTL, that person should write the code correctly. But what if the person makes a mistake, right? Mistakes can always happen. So, after synthesis we had gotten that gate level netlist. This gate level netlist will take it through simulation once again to make sure that this gate level netlist is providing the same output that I desired. We had simulated the RTL. For this RTL simulation, we had used a test bench which was applying the vectors. We can use the same test bench here for this simulation, because the inputs and the values to the inputs can be the same, and ASIC library to tell that when it is seeing an AND gate, what does that AND gate mean, right. So, the gate level netlist that we obtained from synthesis, we will run it through simulation once again, and we will reuse the test bench, so that the same set of vectors are going to this netlist also, and we can verify that the output for this netlist is correct in line with what we had checked at the RTL stage. When we are doing this simulation, we want to verify the functionality. That is what we call as functional simulation. We can also use the simulation to do something that is called full timing gate level simulation, FTGS, full timing gate level simulation. What this means is, when you are doing the simulation, do not look only at the functionality, but also look at the delay through each gate, so that we can see what will be the timing of the entire circuit, whether the CPU can operate at the frequency that it is supposed to operate on, whether the counter can operate at the clock frequency that we want it to operate on, right. So, when we are doing simulation, we did simulation at RTL level, we did synthesis. Now, we are doing synthesis at gate level, first to check functional correctness, and then also to do full timing gate level simulation to check that the timing is also met properly. Lately, lately that full timing gate level simulation is not that popular, and we will see that in a slight while. But let us look at functional verification. So, functional verification we did through simulation. We also use another tool called equivalence checker. Equivalence checkers, you make use of formal technologies. So, you give it the RTL and you give it the gate level netlist, and you tell it, please see if these two are equivalent or not. So, equivalence checker will use formal analysis methods, and it will tell that these two look equivalent. The advantage of equivalence checker over simulation is it does not depend on input vectors. But the equivalence checker major limitation is it cannot deal with very large circuits. So, that is why we have to use both equivalence checker for completeness and simulation, because equivalence checker cannot deal with large circuits. So, for larger circuits we have to go to simulation. In the context of synthesis, we had mentioned that retaining the name is a major care about. We have to make sure that the names which were there at the RTL, those same names are maintained at the gate level netlist. This is to help tools like equivalence checker. The tool can know that what was called count in RTL is count raised in netlist. So, I have to compare these two. Else it does not know what to compare. What was called port in1 in RTL is also called port in1 in synthesis. What was called register R1 in RTL is also called R1 raised in the synthesized netlist. So, it is able to establish some equivalence between certain points, and then it checks whether these points have the exact same logic or not. So, that is for gate level checking, we will make sure that the simulation is working correctly, and we will also do equivalence. So, with these two we will be a bit more reasonably confident that the gate level netlist is functionally correct. We will check timing. Timing checked through a tool called STA, Static Timing Analysis Tool. STA, Static Timing Analysis Tool. It is given the gate level netlist. It is given an SDC file. SDC stands for Synopsys Design Constraints, one of the most popular design constraints format. And the ASIC library. ASIC library contains the delay and the characteristics of each cell. So, the STA tool checks that given the design, given the delay through each element of the circuit, what is the delay for the whole path. From the constraints, you check what was the requirement, and then it can tell you whether those requirements will be met or not. If the requirements are met, that means STA is clean. If the requirements are not met, that means the timing will not be met, and we need to revisit our design to see how to make it meet the timing. STA tool also generates a file called SDF, which is called standard delay format. Because STA tool can do a very accurate timing analysis, it will obtain the delay values and write it into SDF file. This SDF file is used in the simulation. In simulation, when you are doing full timing gate level simulation, you need the timing for each element, for each gate. That timing value will come from the SDF file. So, you do the STA to get the nice SDF file. From the SDF file, you can run the full timing gate level simulation. In general, STA tools are much more popular these days compared to full timing gate level simulation. Many companies have stopped using full timing gate level simulation, they resort more to STA tool. STA tool concepts started getting more popular since around mid-90s, and since then more and more people have much more confidence in the STA tools. By around late 90s, STA tools had become the de facto, the mainline design verification methodology. So, let us look at the little bit difference on STA versus timing simulation. So, most of you have read about setup and hold in your books, and the definition of setup and hold in your books is similar to what we have defined under the simulation category. Setup checks that the signal should not change just before the clock. For certain duration before the clock, setup, the signal should not change. That is the definition of setup as you have read in your book, and that is the definition that simulation uses. Hold definition is after the clock age, the signal should not change for a certain duration, for the duration of the hold. In STA, the definition is slightly different. Okay. In STA, setup means the signal should have reached before the setup time of the clock age. Okay. And this difference may not be so apparent to you when you read these slides, right, but we will explain this difference slightly later in the next slide. Similarly, hold, the STA definition is slightly different. Hold checks that the signal should not reach early enough to interfere with the previous signals. Okay. So, there is a fundamental difference in how the setup and hold is defined between simulation and STA. The main reasons why STA is much more popular compared to simulation is STA is independent of vectors. You do not have to apply any vectors. It will look for all possible scenarios and come back with whether setup will be met, whether hold will be met, whether pulse width will be met, whether period will be met, and so on. It looks at all possible combinations of signals and comes with that STA pass fail. While simulation is dependent on vectors, you have to give the vectors to make sure the appropriate paths are exercised and so on. STA also considers on-chip variation, while simulation does not model on-chip variation. Now, what is on-chip variation? On a chip, the delay through any element is dependent on many factors. Some of those factors are voltage for that element. You should think of an AND gate, right? The delay for an AND gate is dependent on many factors, but at least some of those factors are the voltage of that AND gate, the temperature of that AND gate. And when we were manufacturing the quality of that transistor, whether it was a strong transistor or a weak transistor, all these things affect the delay of that AND gate. Now, think of a chip. On a chip, there will be AND gate here, there will be AND gate here, there will be AND gate here, and so on. Okay. Within the chip itself, just within the chip itself, there might be difference in temperature at various places. So, STA can consider that. that this AND gate could be working at a higher temperature while this AND gate could be working at a lower temperature. Okay. So, the variation on the chip itself, right, that is something that STA can consider, while simulation cannot consider that. Simulation cannot consider that this AND gate was working at one temperature while this AND gate is working at another temperature. Okay. So, let us come back to this difference between setup and hold, difference in setup and hold between STA and simulation. It seems so strange that such a basic thing as setup and hold, right, that also has two different definitions, one for simulation, one for STA. So, leave it here for a few seconds so that you can read these definitions, simulation definition and setup definition for STA definition and simulation difference for definitions for setup and hold. Pay more attention to setup because we can use that as an example. Okay. Changing slide. Consider this circuit that we are showing at the top right side, and there is a clock which is coming in. Signal will start from FF0 and will reach FF1. FF1 should have a setup requirement and a hold requirement. On the waveform, I have tried to show the setup and hold requirement through these two red bars. Simulation says that signal should not reach on FF1 during these red bars. If it comes on the red bar before the clock edge, this is setup violation. If it comes on the red bar after the clock edge, it is a hold violation. This is what simulation says. STA says the signal should have reached before the red bar of the setup. Okay, that is what STA says. Signal should have reached before the red bar of the setup. Now, assume that the signal started at FF0 and reached FF1 just after the clock edge, okay, just after the clock edge, so that it reaches at the time shown by the red bar corresponding to hold, okay, hold requirement. In simulation, this is a hold violation because the signal reached FF1 immediately after the clock edge, right. So, as per simulation, this is a hold violation. As per STA, this is a setup violation because the signal did not reach setup time before the clock edge. Okay. STA says signal should have reached before the setup time before the clock edge, setup time before the clock edge. The signal did not reach at that time. It does not matter after that when will it reach, but it did not reach till that time, so it is a setup violation for STA. For simulation, it is a hold violation because it reached just before the clock edge. If it was further delayed, simulation would not give any violation, while STA would still give setup violation, right. So, this is another reason why STA based techniques are much more popular. First of all, it does not depend on vectors. Secondly, it can model on chip variation, and third, it ensures that the data should have reached in the time rather than it should not have reached at some other time. Okay. So, this is fundamental of say timing analysis that we are doing, STA based or full timing gate level simulation based. Let us now come into concept of scan. I am now changing topic significantly. All this is still RTL based design methodology. You are aware of D flip flop. There is a clock, there is a data pin, and there is a Q pin. Now, think of a mux in front of the D flip flop. Okay. So, this mux we will call as a scan mux. And just like you have Q, you also have another pin called SO, scan output. This mux gets D, a pin called scan in, and a pin called scan enable. What this mux does is, depending on the value of scan enable, it will either feed in D or it will feed in a scan enable pin. scan input value. So, your original design, this flop, original flop and mux, you put it together and you get what we call as a scan flop. Right. So, flop, you convert that flop into a scan flop. The fundamental difference between a regular flop and the scan flop is scan flop, besides getting the D inputs, it also gets an SI pin, scan in pin, and a scan enable pin. The scan enable pin decides whether it will, the flop will capture D or it will capture SI, scan in. Your original circuit can be thought of as what is shown on the right picture with blue line. The flop output Q goes to some combo logic, that combo logic feeds the next flop input D, which goes into the next, the flop's output goes to another combo logic, and so on. But we establish another red connection, the connection which is shown through red line, where the scan output of one flop goes to the scan input of another flop, which goes to the scan output of the second flop goes to the scan input of the third flop, and so on. So, effectively, if I put in a value at scan input of our D flip flop, this scan input can go from one flop to the next flop to next flop to next flop to next flop, totally bypassing the combinatorial logic. Okay. This kind of chain is called a scan chain. The advantage of this scan chain is, if I want to insert a value at a specific flop, let us say some flop very deep in my design, I have very direct path to that flop. I do not have to worry about what kind of combination logic comes into the picture. From primary scan input, I will go and reach directly to that scan flop, that specific flop. This is used a lot for testing. Okay. Effectively, what I have gotten is a very high degree of controllability. I can control the value on any flop directly using this scan path. And similarly, if there is a value onto a flop, I can get that value out to the primary scan output, again using the same method. Keep applying the clocks, the value will keep moving from one flop to another flop. So, I have also gotten a very high degree of observability. Right. So, because I can pump in a value to any specific flop, I got controllability. Because I can we can take the value from a flop to the output, I have gotten observability. Right. So, using this scan path, we have gotten high degree of controllability and observability, and this is used for testing. When we started our presentation, the first slide was you get each die and test it. Okay. Test it how? Using these methods. You put it into the tester, apply the vectors, and those vectors will exercise all the paths that are of interest. You read back the value. If the value is what you wanted, then you know that your device is working correctly, else discard it. The patterns that are used to send this are called test patterns, and that technique is called automatic test pattern generation, ATPG. Okay. So, your patterns will, there will be tools which will generate the automatic test patterns, which is what you will give to the tester equipment. These are very costly machines. So, you want, and then you have gotten this fabrication done, so many devices are coming and you want to test everything very quickly on very costly machines. So, you want your vectors should be such that they are efficient and can test some things very quickly. That is why you add this extra scan based mux and establish scan paths. Now, you may have noticed this means an extra mux for each of the D flip flop, which means extra power consumed and more importantly extra area consumed. We are giving extra area or we are consuming extra area in order that we get high degree of testability. Since we had started with RTL based design methodology, we will continue to show. We had that gate level netlist which we had obtained from synthesis. From that gate level netlist, we will put it into a scan insertion tools which has the DFT scripts, and you will get a scan netlist. So, your gate level netlist had digital logic and D flip flops. Those D flip flops will be replaced by scan variant, which has scan input and scan enable, effectively a mux in front of the D flip flop. and additional connectivity which goes from scan output to scan in of the next flop and so on, and the full chain gets established, right. So, what you get is a scan netlist. Again, there are tools involved for this, from gate level netlist to scan for scan insertion using DFT scripts. So, this is what we were talking slightly earlier, that when we are writing the RTL, it should be written in a manner so that it lends itself, so that the design lends itself easy to ATPG and scan insertion. If I have not written my RTL correctly, even if it is functionally correct but not easy for scan insertion, then my testing will become difficult, which means either more time on the tester equipments or defective chips going to the customers. So, I have to take care of these DFT aspects at the RTL stage itself. That is where tools like lint etc. can help. Let us look at power also. Power is also a big aspect in CMOS circuits, in electronic circuits today. So, what I have done is I have done a CMOS inverter. The transistor is the top is a PMOS and the transistor at the bottom is an NMOS. For those who recollect the basic electronics, PMOS transistor conducts value when the gate is at 0 and the NMOS transistor conducts value when the gate is at 1. So, think of a signal which is 0 at the input of the inverter. So, the PMOS transistor has turned on, supply is now going to charge this capacitor. This capacitor is modeling the load for the next circuit. Right. So, PMOS transistor got turned on, then the PMOS transistor got turned on, the capacitor got charged through VCC and the value at that output has become 1. Now, the input is changing, input is going gradually to 1. Right. In digital circuits we think of 0 and 1, but actually the signals change using a ramp, they do not change abruptly. So, the signal is going from 0 to 1. When the signal is going from 0 to 1, the PMOS transistor is turning off and the NMOS transistor is turning on. In between, for a small duration, both these transistors are slightly on, not fully on, not fully off, but slightly on. That means for that duration, the current will go from VCC to ground, because PMOS is also partially on and NMOS is also partially on. So, the current is going from VCC to ground. Now, the input signal has gone 1, complete 1. The PMOS transistor has turned off, the NMOS transistor is turned on. This capacitor is getting discharged to the NMOS transistor and the capacitor now becomes, this signal now becomes a 0, right. So, this is acting as inverters, right. When initially the signal, the input was 0, the output was high, capacitor was getting charged, finally the input became high, the capacitor got discharged and the output became 0, right. So, this is how the inverter works. But in between what happened, right, in between the capacitor got charged and discharged, right. This is called switching power. The capacitor got charged and again discharged. When the input was changing, for a very short duration, there was a direct path established from VCC to ground when both the transistors were on. So, current flew through that path and this is called instantaneous power or short circuit power. For a small duration, there was a short circuit between VCC to ground, only when the input was changing. So, this is called short circuit power or instantaneous power. Also, when we say a transistor is off, for example, the input is at high, the N transistor is on, capacitor has gotten discharged, the P transistor is off. So, even when we say the P transistor is off, actually there is a leakage current. So, due to that leakage current, the VCC will go through the P transistor and after that the N transistor is also anyways on, right. So, the leakage current is also flowing, right. All these three factors are affecting the power consumption for a CMOS circuit. Okay. This is a switching power due to repeated charging and discharging of the capacitor. The switching power is affected by the value of V, because this energy stored on this capacitor will be half CV square, right. So, the value of V, the value of load capacitance, and the number of times the switching happens, right. So, that will affect the switching power. The short circuit power or the instantaneous power, it is affected by V, because the current flowing will be V by R. The number of times the switching happens, because this short circuit path gets established once during each switching. The amount of time the signal takes to go from 0 to 1, the longer it takes, the longer these two transistors are simultaneously on. If this switches very fast, these transistors will not be simultaneously on for long, right. By the time one is on, the other gets off. But if it goes very slowly, then one takes long time to turn off, the other one is slightly turned on, and so it will take the power consumption will be for longer duration. So, all these I have summarized here on this slide, right. Switching power will depend on voltage because of half CV square, capacitance, number of times that capacitance is getting charged and discharged, and technology characteristics. Okay. The internal power will depend on voltage, because the amount of current flowing is dependent on V by R. The number of times the switching activity happens, the technology characteristics, and the input ramp time. The longer the input took to change, the longer will be the duration of the short circuit power. Leakage power obviously depends on voltage. Circuit state. What does circuit state mean? Circuit state means if the inverter's input was 0, the P transistor was on and the N transistor was off. So, the leakage of N transistor is deciding what is the leakage power. But when that input went 1, the P transistor turned off. That means the leakage of the P transistor decided the leakage power, right. So, that is what a circuit state means, in which different states different transistors will be leaking, and that will decide the amount of leakage power. I had put technology characteristics in each of these. Technology characteristics means the characteristics of the transistor, the amount of current that will flow, the amount of internal resistance that the transistor offers, all those things are part of technology characteristics. So, this is what is the power portion of it, right. This is how power consumption happens. I mean, again, with this little bit understanding of the power, right, we come back to our HDL based design methodology or RTL based design methodology. We had the gate level netlist. This gate level netlist will feed into a power analysis tool. We will give the ASIC library and we will give the SAF file. So, when we give the SAF file stands for switching activity interchange format, right. So, basically this file contains an information as to which design node changed how often, right, because it is very important. The number of changes decides the switching power as well as the internal power, okay, the short circuit power. So, it is very important to get the switching activity, that how many times did each node change. Now, the question is, how will we get that information? How many times did each node change? How will we get that information? Okay. So, that information comes from simulation. When we were running simulation, we were applying vectors. So, simulation can keep track of which node changed how many times and store that information in a file called SAF file. And this SAF file we can provide to the power analysis tool. It already knows the design because it has a gate level netlist. It knows the technology characteristics because it has the ASIC library, and it got the activity related information through the SAF file, right. So, again, power analysis will happen much later, but if your RTL is written in a manner so that it does not consume so that it is not power efficient, right, we will get to know at this stage. It is much better to know it upfront, and that is where the RTL design expertise and so on will come, right. Your RTL should be written properly. So, what we did was we wrote the RTL, we verified it in simulation, through static checkers, through assertion based tools. then we synthesized it. After synthesis, we did the functional verification using simulation, we did equivalence checker. After doing functional verification, we did the timing analysis based simulation. Sometimes we do timing analysis based simulation, these days not very popular, but we will do STA. We did the STA, after that we did the DFT, the scan insertion, converted the flops onto scan flops, so that this design when implemented on the hardware will be easy to test, and that DFT based netlist will do power computation. So looks like there is a question on phone, we will take that question. Hello?
Hello, good morning, sir.
Good morning,
My
ma'am.
name is Meghna. I am calling from Warangal, sir.
Yes, Meghna.
I have a doubt on power consumption, what you are telling on that, sir.
Yes, please
My
go.
question is, how to reduce the dynamic power consumption of a design, sir?
Okay. So, Meghna, the word you used was dynamic power, and dynamic power is a combination of switching power and internal power. Okay. So, these are the various characteristics around which we can play to reduce the dynamic power. Okay. One of the most commonly used techniques is clock gating. If you look at it in your circuit, the clock keeps on coming at a very regular interval and is the highest frequency switching signal. Right? The data signals don't switch at the same frequency as clock. Okay. So, if you know that there are portions of your circuit where you do not expect any activity, you can do the clock gating in those portions of the circuit. That is one method. The other method is what is called as voltage isolation. If you know there are portions of the circuit which are not going to be used at all, you can prevent the voltage supply from going over there. Right? These are two very common methods, or what I should say is methods which provide large scale power saving for dynamic power. Okay. Each of these has its own nuances in terms of how to do it, things that you have to take care of, etc. Then there are some local kind of things, right? For example, if you think of a multiplexer, if you think of a multiplier, okay, a multiplier is made of a lot of XORs. XORs are usually very power hungry. If you can replace a multiplier by something else, sometimes that may be possible, then you can save some power. For example, if you have to multiply something by 2, you can just do a shift, right? You will get a multiplication by 2. Okay. The reason why XORs are power hungry is if you look at AND gate, okay, AND gate, let us say some input changed, the output may or may not change depending on the input, the other input being 0 or not, right? If you look at an OR gate, if an input changes, the output may or may not change depending on the other input being 1. Okay. But if you look at an XOR gate, any input that changes will always result in output change. Okay. So, XORs are power hungry. So, like I said, some of the smaller things you can do is see if you really need an XOR or can you do with something else. The multiplier getting replaced by shifter was one example. But the bigger hammers to use are clock gating and circuit isolation, which we also call as voltage island. Identify portions of the circuit which are not supposed to be active and turn off the power over there and bring it. If you look at your laptop, for example, right, when the laptop detects that there is no activity going on, your screen turns blank, right. So, those are the kind of activities it is doing to save power. Okay. So, and then there are other things also. For example, right, with capacitance also you can play with. Look at an AND gate. On an AND gate, both the inputs are interchangeable. Okay. So, if I find that the capacitance of pin A is higher than capacitance of pin B, then the higher frequency signal I will try to connect to pin B rather than to pin A. Okay. But the power saving will be very, very small. Okay. Some of those are more theoretical than actually practically used. Practical usage is clock gating, operand modification or operation modification, voltage islands isolation. Okay, I continue. This is where we did the power analysis. Okay, I had talked little bit earlier about limitations of RTL based design methodology. That time we talked about how somebody could make a mistake in writing the RTL code, and then we explained that the solution to that is that people should know how to write the right RTL code and write it correctly. They should use correct tools which can look forward and tell us problems which can happen further down the road, right? But let's talk about some other limitations of RTL based design methodology. Not everything can go through RTL based methodology. Okay, these are things which cannot be implemented using digital gates. Analog blocks, for example, right? Analog blocks cannot go through RTL based methodology. Memories. Many of the people think that memories you can implement using flops, but that's not correct. Memories are much more denser. If you try to implement using flops, you will get such huge memory, while actually they are very, very dense. So memories are usually done through individual transistor level thing or using memory compiler. They don't go through digital logic circuits. Okay. If there are high performance data paths. Okay. So looks like there's one more question. Let's take that question on phone.
What are the important topics to prepare a partition to track?
Sorry, I don't think I could hear your question properly. Can you please repeat?
Okay. What are the important topics to prepare in RTL design to crack an interview?
Okay. So if you want to crack an interview, okay, learn at least some HDL, okay, be it Verilog or be it VHDL, okay, and also when you learn, just reading the books won't help. Okay, learn the language and practice using some tool. You can use a synthesis tool or a simulator tool or any of those design analysis tools. Okay, most of the design analysis tools will be reading Verilog or VHDL. What happens is a lot of students, they think that when they read a book, they can come prepared by reading the book and they can manage the interview. That doesn't happen, because most of us interviewers, we don't ask questions based on what should work. Okay, we ask questions based on what should not work. Okay, only if you have tried and practiced, you would have seen something that does not work and you will be able to tell what does not work. Okay, so read any book on Verilog or VHDL, okay, and practice the examples there and try to play a little bit with modifications of the examples to check what you have understood works correctly or not. You will see errors, absolutely fine, try to debug those errors and so on. See, don't think of cracking the interview, okay, think of learning that topic, then you will crack the interview anyways. Okay, have some basic knowledge of digital logic, that will help. Okay, so I'm coming back to this slide now. Analog blocks, memories, these cannot be realized, these are not realized on digital logic. So RTL based methodology does not work for these kind of designs. If there are very high performance data paths, theoretically we can do it through digital logic and hence through RTL, but typically these are done through custom layout, because these are very high performance. So typically these are done through custom layout. People who are very, very experts in these high performance data paths, they will do a custom layout design, each individual transistor being handcrafted and so on. So what do we do about these kind of blocks? These blocks which don't lend themselves to RTL based design methodology. So for simulation, we can still write, say, behavioral model or switch level model, etc. And for circuit realization, it has to be handcrafted. We cannot use synthesis. RTL we had used for simulation and for circuit realization, but these kind of blocks we'll write behavioral models or switch level model or whatever, and realization we'll do through handcrafting. Now the next question is, if finally I have to realize my circuit through handcrafting, why do I even need the RTL for this block? Okay, what is the use of an RTL? If memory I am going to do handcrafting, I am not going to use synthesis. Why should I write the memory model for? Why should I write the HDL for memory? Right? Why should I even write the Verilog code for memory? because I cannot use that code for my circuit realization. Right? So, if I am not going to realize that circuit, why bother about writing the HDL? Okay. Now, my design has lots of blocks. Okay. 9 of those blocks I can go through its RTL, but one block I cannot go through RTL. Okay. For me to verify those blocks, I need the whole design in HDL. That is why for simulation, right? And that is why for this 10th block also I might want to write an HDL, not the RTL but the HDL. I might want to write the Verilog code for this 10th block also, so that the other 9 blocks can be verified, so that my simulator can have a view of the full design, full system. Else the simulator can see the 9 blocks, but the 10th block, what do I do for the 10th block? How do I simulate the whole design? Okay. So, that is what I meant by, so that other synthesizable blocks RTL can be validated in situ, right. The other one is this second usage is not very common, okay, but something for you to consider. We have used this in the past. Let us suppose you have a friend who is working on this custom block, analog block, and that friend has to also verify that custom block. For verifying of that custom block, that friend is running SPICE simulation or EPIC simulation, whatever, right, and they have to give lots of zeros and ones. Think of an 𝗧-𝗦𝗔𝗧 model. Those who are familiar with 𝗧-𝗦𝗔𝗧 model, these are 2 wire models. There is a clock and then the data line. On the data line, you send everything on the data line, the start of the protocol, the command, the address, the data, okay. And we have seen 𝗧-𝗦𝗔𝗧 designers counting 0 0 0 0 1 0 0, oh this is read, okay, address 0 1 1 0, okay, this is this address, and right, it is so painful. You imagine, right, doing all this counting yourself, right, so painful. You can help your friend, write the HDL model for it and provide higher level of code and get that HDL model to dump out all zeros and ones, okay. So, for example, you could tell in memory, write the value such that each address gets the same data as its address value, right. It is very easy to explain that, and tell that Verilog model to dump out the values in zeros and ones, which is something that your memory model designer friend can make use of. So, you can get some friendship with him, right, tomorrow it can be useful. So, the point is, even if a block cannot go through synthesis because it does not lend itself to RTL based design methodology, it may still be worthwhile and useful to create HDL for that block, so that this block sits along with other blocks and you get a complete view of the complete design, and also so that this HDL you can use to create lower level zeros and ones which can be used by the analog designer. So, some of the memory model designers are my friends because of this reason, because I have helped them in this way in the past. Okay. Some more limitations, lack of control. You cannot control at each transistor level. So, that is why you cannot do custom sizing of each transistor, and this is why high performance data path usually go through custom design mechanisms rather than RTL based mechanisms. We depend on synthesis. Since we depend on synthesis you had seen was making use of ASIC library. In ASIC library, what will happen is, for example, AND gate, right. We will have 3 or 4 variants of AND gate with different drive strengths, okay. So, the synthesis tool will pick one of these depending on what best suits the optimization requirements. So, effectively AND gate drive strengths, which could theoretically be a continuous variable, is effectively becoming a discrete variable also, okay. So, you have to depend on a few variants for each type of gate rather than something which you could choose in between also. When you are doing custom layout, you can decide the length and width of each transistor on your own. Synthesis technology does not say that you can use only, you have to use only 4 AND gates, you have to use only 4 OR gates and so on. But practically it has been seen that if you have 2 to 4 variants of each kind of digital gates, that is more or less sufficient to provide most common usage design realization. Okay. RTL based design methodology does not support voltage levels. Okay. There is a question on the phone, but let me finish this thought, right? Voltage levels are not simulated. There was a question earlier from Meghna, and we talked about you can use voltage islands, etc., right? But if you want to simulate voltage islands in RTL based methodology, that possibility does not exist, because there is no explicit voltage signal. So these are some additional limitations of RTL based design methodology. Now let's come back to the question. Hello, what's the question? Let's go to the question.
Hello.
Yeah, please go ahead.
Yeah, sir, I have one question, sir, on VLSI.
Yes.
Sir, how many areas are there to start a career in VLSI, sir?
Okay, so I'll come back to this question, right? You said how many areas. It is difficult for me to say how many areas, but I'll cover some of the areas, okay, towards the end of my presentation, which I am coming in a few minutes, okay. But just to provide some perspective, when I initially started, we talked about the post wafer, okay. Then we said the fabrication, okay. Those two areas I have never worked, okay. Then we came to the design aspects of it, and we said this logic design, physical design. There we had some 6 or so blocks. I have spent 31 years only on 2 of those blocks, right? The logic design and so on. Whatever I am talking about, these are the areas that I have spoken about, right? That's what I am trying to say is VLSI could be a lot of areas. I have spent 30 years working in just 2 of those blocks, okay. So you can imagine how many more areas, and within those 2 blocks we have talked about so many things, okay. So let me go to my next slide, and this answers your question. This is my last slide, okay. If you want to look at a career path in VLSI industry, okay, there are that manufacturing side definitely, but among the topic that we talked about, the topic that we talked about was probably 1/3 or 1/4 of one area, and there are 3 such areas, right. So for those 1/3 area, you could work on EDA tools. EDA stands for electronic design automation, okay. We talked about all those various tools: simulator, synthesis, timing analysis, formal checker, ATPG tools, power tools, placer, router, which we didn't talk about, right. So you could find a career in one of these tools also, right. You could work in any of these tools. Companies like ours have EDA tools. Companies like Synopsys, Cadence, Siemens, or Mentor Graphics, they work EDA tools. ANSYS works on EDA tools. There are lots of companies that work on EDA tools. You could work on RTL design. The person who is going to write the RTL code, right, the HDL code, you could work on RTL design. You could work on design verification. We talked that you have to run a lot of simulation to verify the designs, right. You could work on power aspect of it. You could work on design for testability, the scan insertion, the pattern generation. You could work on timing analysis. You have to make sure that the design meets timing, the timing requirements are conveyed correctly. If the design is not meeting timing, what changes should you make so that the design is able to meet timing. Physical design means the placement and routing, that aspect of it. You could work on ASIC libraries. These libraries contain the information for each of the gate elements, okay. So any of the ASIC houses will generate ASIC libraries. So looks like there is one more question. Let's take that question before we can explain further on some of these career paths. By the way, this is my last slide, right? So we can take as many questions as we for the next 10 minutes or so. Sorry. So hello, what's the question? Let's say the question.
Good morning, sir.
Good morning, ma'am.
I'm Nivriti from Maychel, sir.
Okay.
I have completed my BTech.
Yeah.
And if I need to start my career in semiconductor design, could you please guide us and how to go in that?
Yep. So again, I didn't get the name of the college. What happens is a lot of semiconductor design companies, they go to various colleges for campus interviews. Okay. If you have a company which is coming to your college for campus interview, that is your easiest and best possible path. Okay. If that doesn't happen, then the other possible paths could be you could join some of these finishing schools which are doing training specifically on semiconductors. From there you could get into one of the semiconductor companies. third possible path could be you could join some smaller companies which work in semiconductor area, and they can provide you a head start, and or they could provide you a path to start. Once you get some experience, then you can join some larger companies. Please understand that semiconductor field is usually a very lucrative field in terms of good salary, good work environment. Typically, good salaries are good or work environments are good. So, a lot of these companies are also very choosy in terms of where they will be able to go. And plus, we can only recruit so many people, right? We cannot recruit. There are so many colleges in the country. We cannot recruit from all the colleges. So, we have to be also choosy in terms of where we can go, where we can spend time, right? We cannot go to so many colleges. So, to start with, look at these paths. Any company coming to your college, or do a master's from a better college where some of these companies can come, or go to a VLSI training institute from where these companies will recruit, or start with a smaller company which would be less choosy, get some experience, learn something, and then after that it's easier to jump into a larger VLSI company. These are the paths that I am aware of, or that I can think of. Okay. So, continuing down this path, right, basic libraries, you can do the cell design, you can do the IO design, you do the characterization and modeling. Characterization and modeling means for a given AND gate with what kind of input ramp time, what kind of temperature, what will be the delay, what kind of output load, what will be the delay, and all those kind of things, right. You characterize, we used to characterize and sell across some 64 different load types and some 17-18 different input ramp times, and then do it across few temperatures and so on. Tons of spice simulation over several days, right. So, that is called characterization. Depending on different input characteristics, what will be the delay, what will be the capacitance, and so on. And then you have to create a model which will capture that data, so that all that can go into ASIC libraries. You can also be a domain expert. All these semiconductor VLSI is used towards something. For example, wireless applications, for example, machine learning applications, for example, emulation devices, for example, climate change studies, okay, for example, autonomous driving. So, you can be a domain expert also and go into that path also. And then things like manufacturing, packaging. I mentioned manufacturing, packaging only because we are starting to see some of those companies coming up over here. I mentioned ASIC, Keynes, there are announcements by Micron, there are announcements by Tata. So, there are several companies which are announcing the manufacturing and packaging industry starting in India also. So, you can look at those, you can look at research labs also. So, these are few career paths that came to my mind strictly on VLSI side. Then you have related fields, for example, embedded, which itself is a huge area which interacts very closely with VLSI, right. I think with this I come to the end of my prepared presentation. If there are some additional questions, we can take few more additional questions for a few minutes, and then we will close, right. Okay. So, thanks a lot for your time. We will see you again during the next session. It will be done by another colleague of mine. Thank you very much for your time.